more. I think some people are still trying to connect. Thank you. Well, I think we can start. Well, hi everyone. Thanks for meeting us here today. We are receiving Angela Zhou from the Cornell University. She is a PhD student in the Department of Operational Research and in Information Engineering. And she's gonna talk to us about a work she participated in the last year, entitled Assessing Algorithmic Fairness with Unobserved Protected Classes Using Data Combination. Thanks for joining us, Angela. For people following us on the YouTube streaming, I'll try to follow if there are some questions. Angela and I agreed that any one of us here in the room can just make interventions or asking for clarifications during the presentations, but we are gonna keep the longer questions, like the most fundamental questions, like to the end of her presentation. Thank you very much. Angela, if you would like to begin.
Okay, sure. Thanks for the introduction. It's really great to be here. Let me just share the right window. Okay, so can you see my slides? Is this good?
Yes.
Okay, great, thanks. Yeah, it's really exciting to be here and give this talk. I'll be talking about this paper, which is joint work with Nathan Callis and Xiaojie Mao. This work is about trying to develop methodology for assessing algorithmic fairness, like the title says. And so for a brief overview for this talk, I'll just try to introduce some of the background of the problem and some motivation, and then I'll introduce our method and our approach. I'll walk through some of the results and talk about some computational issues or statistical estimation issues, and then I'll conclude by kind of showing a couple of case studies that we developed to illustrate this approach. And so what is the story of this paper? Well, quite often in practice, it's really important to try to assess disparities in data. And what is a disparity? It's a difference in some outcome that we care about that is different across members of some group. And we're going to call that the protected attribute. I'll be more formal about this later on in the problem setup. But often in practice, we don't actually have access to to the protected attribute in the data that we want to assess these disparities on. And so our paper is really trying to tackle this problem and try to understand what are the limits of any conclusions that could be made in a very common setting where you might have access to a proxy method or some additional information, such as census information. And so we're going to study this question of if I have a predictor of the protected attribute given extra information, how far or what is the range within which the disparities can lie. And the kind of takeaway of our study is that we're going to provide some sets of where the disparities can be. So just a quick preview of what our results are going to allow people to do is that you can make a statement that the disparities lie in these rectangular regions, but you have to make additional assumptions in order to be able to make a conclusion that a disparity is any particular point in this region. So the true unobserved disparity is this red star. And with the proxy information that we have available, just income or geolocation, we can't actually make any conclusions about disparities other than they lie somewhere in this region. And so what is the practical purpose of providing these kind of set estimates? So either these sets are going to be small, so they allow you to rule out the presence of certain disparities, or they're going to be very large. In this case, they're a bit large, and that suggests that instead you should improve the proxy methodology. So that's a kind of preview of the story of the paper, and I'll try to fill in the details later on. First, I'll start with some background on the setting, and I'm going to talk a little bit about lending discrimination. And unfortunately, this background is going to be kind of very US-centric, just because that's the setting that I'm familiar with. And I'm not an expert on these kind of regulatory aspects either. So I'm going to be trying to highlight how this connects to the kind of broader discussions in algorithmic fairness. And so, of course, assessing disparities is really important. It's so important that it's regulated by law. In the United States, there's the Equal Credit Opportunity Act and the Fair Housing Act, along with other kind of financial regulators that are very interested in these aspects of consumer protection. And so there are a lot of regulations that prohibit discrimination in credit lending as well as kind of residential real estate lending. And how do we kind of think about discrimination? Well, again, there's this idea of some protected attribute, which is some kind of aspect of a person's identity upon which we want to ensure systems are not discriminating against, whether on the basis of kind of individual behavior. So whether kind of individual people with discretion can distinguish or make different decisions on the basis of these protected attributes, or even just by systems more broadly. So protected attributes can include things like race or color, religion, national origin, sex, marital status, age, and other kind of markers of identity that we want to provide consumer protection for. And how do we think about discrimination? There's kind of two broad categories. The first is disparate treatment, and that happens when there's evidence that the protected attribute was taken into account in some individual decision-making process. So if a kind of individual lender is taking race or religion into account when making decisions, that results, then that can be considered as evidence of disparate treatment. And this is about the kind of procedural fairness of the kind of system or the lending process. And another main category is disparate impact. So this paper is going to be focused on kind of quantitative measures of disparate impact. So disparate impact arises when a lender or a bank is applying a kind of relatively neutral practice equally, but it happens to disproportionately exclude or burden certain persons on a prohibited basis. And so, for example, if a lender is applying some lending rule uniformly across the board for all the customers it sees, So even if we don't have kind of individual racial animus or individual intention to discriminate, if this practice happens to result in unequal burden on members of different groups, then this too is a discriminatory practice, and there's kind of legal protections against this occurring. And so again, the process for these kinds of claims is that, if a regulator initiates a claim of disparate impact, the lender has some opportunity to show that, perhaps this practice was justified by business necessity. So for example, if there is a disparity in the amount of loans given across race groups, the lender might have recourse to say it was business necessary on the basis of kind of the estimated credit scores or some kind of business necessary factor that resulted in these disparities. So that's the kind of broad picture of discrimination as it's discussed. And again, there's just this important point that actually these same discrimination regulations actually prohibit creditors from actually asking about the protected attribute. This is one way of ensuring that there isn't disparate treatment in your processes, is to make sure that you're not collecting the protected attribute. However, and here I'm pulling from a document from the Consumer Financial Protection Bureau, which is actually talking about how they use proxy methodology. Of course, in order to be able to estimate disparate impacts or kind of audit lenders and creditors for these claims, one needs to have access to the same protected attributes that one wants to kind of protect against discrimination against. And so in the financial sector, there's this kind of fundamental problem where we are interested in protecting against disparate impact, but in certain areas, this information is not recorded. And so what is the industry standard for regulators? So this report by the CFPB kind of discusses this idea of using proxy methods. So one famous or infamous method is called BISG, Bayesian Improved Surname Geocoding. And the main idea is that we're going to try to predict an individual's race based on information about their zip code and surname. So in the American Census information, we might have data of individual households, the self-reported race ethnicity information, and we have access to this other information like zip code and surname. And the idea is to somehow try to use this probabilistic prediction to try and fill in the gap. And so just the main takeaway from this background is that it's often the case that the protected attribute information is not available in the data. And people are really interested in trying to fill in this gap with proxy methods. However, these proxy methods can be controversial. And so I want to highlight some related work by Chen et al. 2019, including some co-authors on this paper, Xiaojie Mao and Nathan Callis, where they kind of study a specific threshold-based rule that uses this probabilistic prediction to try to audit disparities. And they show that this commonly used threshold rule is kind of statistically biased. And so this is a bit of an issue because now the use of proxies to measure disparities can make a claim of auditing disparities vulnerable to criticisms of the proxy method. And there's a little bit of a sense in which it's like a little beside the point to introduce this vulnerability. And it's also a kind of, this has happened in the past. So the CFPB initiated a claim of disparate impact against Ally Financial for indirect auto loans. Ally Financial eventually settled, and this claim was initiated using the BISG proxy to estimate the disparities. And when they sent out the settlement checks, they still didn't actually know who had been discriminated against. So they also sent out the settlement checks to people on the basis of their estimated race membership rather than their kind of actual race membership. And this process was criticized in a congressional report, in part because of their use of this proxy method. And I don't know all the details about the controversy. They were probably also responding to other things, but at the very least, using these proxy methods is statistically biased and controversial. And so studying kind of really what is happening with these proxy methods is important to get a better understanding of this kind of statistically difficult task. And so I'll just briefly mention some related work. And so the main related work is this paper I mentioned by Chen et al. 2019. And it studies this question of certain classification-based rules or threshold-based rules for estimating disparities. And so once we have this probabilistic prediction, there's a question of what is the estimator we should use to try to estimate these disparities. So this previous work studies the statistical bias of a few commonly proposed estimators. Our work is going to be a little different because we're going to study the fundamental identification limits of the problem, and we're not going to focus on any particular estimation technique. And in terms of approach, our approach is very much so drawing on some work on data combination in econometrics, as well as partial identification. So these are ideas from econometrics. Okay, and so now I'll start setting up the problem formally. I don't know if there are any questions about the background or motivation. I just wanted to pause in case there are any questions. But if not, I can talk about the problem setup.
Hi. You mentioned that the proxies like the zip code and the surnames are biased. Have people measured how biased they are, or do you know what they're biasing for or against?
Yeah, so that's a great question. So unfortunately, I don't have the citations on this slide. So BISG, even if the statistical prediction of race based on these proxies is unbiased, the issue really arises when trying to use this proxy method to actually estimate the disparity measure. So even with perfect prediction, with this proxy method, certain kinds of estimators that are rules for using the proxy to estimate disparities are going to be statistically biased in the absence of strong assumptions. So it's possible that the prediction of race is statistically unbiased, but the way you use it to try to estimate these disparities can introduce bias.
Okay, thanks.
I think we can move on.
Okay.
I think you're good to go.
Okay. Okay, so throughout this paper, I'm going to talk about like a classification setting. So I'm going to allow there to be kind of two outcomes of interest. Y hat is going to be a historical decision, such as whether or not a loan was originated for some individual. Y is a true underlying label or outcome, whether or not an individual actually defaults on a loan, for example. And then I'm going to let A be the protected attribute. So this will be binary and multiple level. And Z is this auxiliary information that's used to train a proxy method. And so again, now formally, the goal is to characterize the boundaries of what we can conclude in the setting where we also have access to an auxiliary data set. So I'm going to assume that our problem information, we only have access to it in this kind of segmented fashion, where we have a main data set, where we have information on outcomes and the auxiliary information. So in the lending case, it's the data set where we have access to loan outcomes or defaults, as well as income. And this auxiliary data set is the data set that contains race information. So we have another data set where we have race and income information, and this can come, for example, from the census. And so that's the data combination setup. And now I'll briefly kind of talk about binary classification. And so in binary classification, of course, we have some covariates X, we have some predictor Y hat, and we have a true outcome. And so I won't go too much into detail, but in classification, algorithmic fairness, one way of trying to formalize it is by considering differences in errors across groups. And so we're going to focus on disparities that are commonly studied in algorithmic fairness, such as demographic disparities. So if y hat is the amount of loans that are actually given to people, demographic disparity is simply the difference in the number of loans that are given to people of different groups. And so this may not be the most meaningful notion of disparity because there could be different reasons why members of different groups are not given loans. It could be due to differences in income or creditworthiness. And so in algorithmic fairness, there's this idea of trying to study classification-based disparities. So conditional on the kinds of information that would justify a loan decision, which is like the true outcome of an individual. Are they going to pay back a loan or not? Does a classifier for whether or not they pay back a loan have different error patterns? Does it kind of overestimate the loan payback rate of one group versus another? And this is sometimes referred to as a true positive rate disparities. And throughout, I'm going to let little delta kind of denote disparity. And of course, there are a lot of ways to measure error for classification. You can talk about false positive rate disparities, but I'm going to present our approach for true positive rates. And it's kind of easily adjustable to these other notions of error rates. And yeah, so true positive rate is simply one metric by which someone could be interested in auditing disparities. But we're going to focus on that with the understanding that it's relatively straightforward to extend to other error rates. And so again, the key problem is that we don't observe A in our data. All of these quantities are, very easily estimable if A were observed. But now we're actually going to be conditioning on an unknown quantity, and that's going to be the main technical challenge. And so again, just to highlight, what is it that we can estimate? We can estimate the probability of loan default given this auxiliary information Z, and we can estimate the probability of race membership given the same information. And so the question is, how do we actually kind of obtain additional insight from these two separate prediction tasks? And again, what we want to estimate is a function of all of this information. And so I kind of mentioned identification a lot. And so let me try to introduce it intuitively. So for our measures of disparity, delta, we're going to try to study the partial identification set theta. And the partial identification set is the set of all of the possible values for the disparity that are compatible with the data that we observed. And the data that we observed allows us to estimate these two different prediction models.
Could I ask you to go back to the last two slides and run by it just just one more time? I think I'd like, yes.
Oh, sure, yeah.
I'm just trying. Could you just like make another run of this slide, please, if you could?
Sure. Yeah. So so in this setting where we have access to two data sets, what we can estimate from the main data set, and this is the setting where we have access to loan outcomes and income, we can kind of try to build our classification predictors or our kind of lending predictors of whether or not an individual defaults based on this auxiliary information. But we can't directly audit these prediction models for the errors that would be incurred by different groups. On the other hand, from our separate auxiliary data set that has access, that has information about race and income, we can estimate the probability of being of a certain race based on this auxiliary information. But we're going to be focusing on the case where we can build these prediction models from these two data sets, but the individuals are not the same in each data set. So this isn't a kind of database join problem. So this isn't really about like a probabilistic join or a record linkage. These data sets could actually be comprised of completely different individuals.
Thank you.
Yeah, and so these are all the kind of like probabilistic quantities that we're going to be working with. In some sense, you can think about the ideal setting is we have the full distribution on A, Y hat, Y, and Z. This is this top true joint distribution. However, our two data sets mean that we only have access to certain subsets of marginal distributions of this joint distribution. So P, Y hat, YZ, P, AZ, those are two data sets, and they give us two partial views of this full joint distribution.
Thank you.
Yeah, and so with those quantities in mind, we're going to be focused on the partial identification set of all of the disparities that are compatible with our observed data. And so the disparity measure is going to be some kind of statistical functional of the full joint distribution. And we don't have access to that. We have access to certain marginal distributions of it. And so importantly, this question of identification is independent of the actual estimation strategy. So it's possible to make additional assumptions, come up with a certain kind of estimator that recovers a certain disparity within the set. But essentially, in the case that this partial identification set is not a point, it actually means that there's a lot of kind of remaining ambiguity of the problem, because if a procedure reports a point estimate, typically you don't actually have information in your observed data to kind of tell you which point estimate in this set would be better. They simply correspond to different additional assumptions that could be made. Some of these additional assumptions might be more plausible in certain kinds of settings, but this question of partial identification is kind of the first step in establishing what can we say without making any further assumptions on the joint distribution that connects these two data sets. And I just wanted to pause for questions on the setup before I talk about our kind of specific method or approach.
I don't know if I understand, if I actually understood the differentiation between phi being a set or a point. Could you explain this again, please?
Yeah, sorry. So in the case where we observe infinitely many samples, this is kind of a question of whether our statistical procedure is kind of uniquely identified based on the observed data distributions. And so it's kind of about, if we think about the disparity, this underlying disparity as kind of giving rise to a data generating process, it's about whether or not we can recover the generating disparity from our observed data. And we're going to be focused on the case of partial identification, where there are actually many disparities that could have resulted in the same observed data. And that's the kind of meaning of partial, so that we can't fully kind of invert from the observed data to the underlying statistical parameter.
Okay, thank you.
Okay, so I'll talk about our method. And so at a high level, we're going to just optimize over the under-identified parts of our probability model. So we're going to represent the unobserved probability distributions as optimization variables. So, and we're going to use the fact that probability distributions satisfy certain properties and simply optimize over this range. And so the main properties that we're using is kind of simply representing and simply optimizing over these probability representations. And so I'm going to start with a case of estimating a marginal disparity. So the conditional probability that y hat equals 1, given a certain group value u for a kind of generic group. And so I'm going to use Bayes' rule. So this numerator is a different way of writing the joint distribution of y equals 1 and a equals u in this special case where the outcome is binary. And the denominator is actually just the probability that a equals u, but iterating over the outcomes and auxiliary information. And so why do we kind of expand this probability and extract these kind of conditional probabilities? Well, we want to isolate the term that's unobserved, but if we observed it, would actually recover the disparity that we're interested in. And it's the probability of race membership, given both the outcome and the auxiliary information. And so this is observable if we had all the information, but again, we never observe any single row that has all of this information. And so this is some unknown probability. And we're going to parameterize our analysis with respect to this unknown probability. So we're going to just consider as a generic unknown function of any value of y hat and z. And so now we can consider the case. So, and I'll talk about like what are the properties that this unknown function satisfies. So in our setting, again, the blue and the red correspond to the probabilistic information that is estimable from our data set. And it's generated by, in gray, this unknown probabilistic information, which is a rewriting of this unknown function that I wrote here. And so although this probability is unobserved, we know that it actually marginalizes to the proxy, to the kind of proxy probability of race. And so this is simply the law of total probability, where it marginalizes out the outcome information. And so that's kind of another way of recognizing that one of our data sets has implicitly marginalized over the information in the other data set. And this will allow us to, this imposes some restrictions on how crazy this unknown function can be. We know that for every value of z, this unknown function satisfies this first constraint of the known marginal distribution. And further, we know that this function is a probability distribution, so it sums up to 1 over groups. So every individual has probability 1 of being in one of all of the possible values of the protected attribute. And this function is bounded between 0 and 1. And so again, this is not making any additional assumptions on the structure of the data, but it will turn out to allow us to still place bounds on the disparity level. And so I guess to highlight how we translate this into an optimization problem, I'll just write out the optimization problem for a single group. So we're going to optimize this estimate of the unknown disparity over the range of the unobserved probability distribution, subject to the constraints that all probabilities must satisfy. And so this there is kind of classical literature on this. I don't know if you're familiar with Fichet-Hufting bounds, or if you're familiar with risk management in finance. Copula theory is kind of concerned with similar ideas. So if you have two random variables in a portfolio, but with unknown correlation structure, what is the kind of like worst case versus best case expected return if you don't have any information on the copula that kind of governs the joint distribution of the members of your portfolio. And the maximal and minimal correlation structure is well studied in these very classical Fichet-Hufting bounds. And so our paper is going to kind of build on the modeling for this. We're going to use this optimization framework to add further complexity and handle more difficult estimation. And so I'll summarize some of the results in the paper. And so we handle demographic disparity as well as TPR or classification disparities. And so as we change rows, as we go down this table, what happens is that the statistical estimator becomes harder to optimize. And as we change columns, what happens is that we're kind of allowing more complex modeling. So instead of just a binary protected attribute, we can also add additional assumptions on the probability distribution, and we can also handle multiple valued protected attributes. And then we can think about the combination of additional modeling complexity and kind of more complicated estimation. And so this is a kind of sketch of our results. So we obtain closed form bounds for some of these cases. In other cases, we can write or reformulate this as a linear program, which is kind of computational solvable, even if we can't write down closed form bounds. And in the most complicated case, we provide a kind of generic algorithm that allows you to reduce this to linear programming, although it itself is kind of hard to optimize. And so I'll just kind of walk through the results. We first kind of verify that the joint distribution is not identifiable from the observed data, and neither are the disparities. And connecting this to previous work, there's only really very strong and not practical assumptions under which this becomes identifiable. And then I'll talk about, first I'll illustrate the closed form bounds for this case of a binary value protected attribute and demographic disparity. And so this is our optimization problem. Actually, the denominator is the probability of A equals B. How do we obtain this probability of race? We can actually take our predicted probability of race and marginalize over the distribution of auxiliary information in our main data set. So this is no longer an optimization variable. And what this means is that, and here I'm going to try to set this up as just an optimization problem. So I'm going to generally allow the set of constraints corresponding to the set of all probability distributions consistent with the data to be denoted PD. And I'm going to let PA do the set of additional assumptions. And it's going to be parameterized as some kind of weight function. And so I'm going to shift to referring to this unknown probability as just a function WA. And this is a function of y hat and z. And so this just allows us to highlight the kind of optimization structure. And so in the closed form case for demographic disparity, what happens is that you simply maximize the weight function for the first group, and you minimize the weight function for the second group. Now, what are the maximal and minimal values of this weight variable? Well, you can actually compute them, compute these maximizing functions directly. They're given in the closed form structure here. And this is also exactly, again, the Fréchet-Houghton, it's very similar to the Fréchet-Houghton bounds. And so briefly, I'll talk about how we construct the program for the more complicated case of the true positive rate, where we are, again, somewhat surprisingly able to obtain closed form bounds. And so the main difference when we look at classification disparities or true positive rate disparities is that there's now uncertainty in the denominator. And that's because classification disparities, if we think about disparity as a conditional probability conditioned on group membership, for a classification disparity, we condition on both group membership as well as the outcome or some level of the outcome. And again, we never jointly observe the protected attribute and the outcome. And so that's why there's now uncertainty in the denominator. So this is no longer a simple linear program, but it's actually a relatively standard, it's a linear fractional program. So I won't go into the details are in the paper, but for this kind of structure, for the difference of two fractions, we can reformulate this to a linear program. And it turns out that for a binary valued protected attribute, this actually has closed form bounds. So in this special case, this has closed form bounds. But as we add modeling complexity, this will be a more non-convex program. So the main takeaway from the slide is that we introduce difficulty because there's uncertainty in the denominator of this conditional probability. And that's the main difference in going from a demographic disparity to a classification type disparity. And so now I'm going to talk about some extensions to the model. So we're going to kind of move across this diagram across the columns. And so one extension is that we can assume that this unknown probability function is actually smooth in Z. And why might this be kind of plausible? Well, we might simply expect that the probability of race membership, given a continuous variable or a continuous z like income, is actually smooth in the proxy. So we don't really have discontinuous jumps. So that's a kind of intuitive and intuitively justifiable explanation. However, if we look at the Fréchet-Hufting solutions for two groups, in general, this solution is going to be pretty non-smooth in some points. And this is, if we kind of go back to Copula theory, we know that the optimal worst case and best case copulas correspond to correlation 1 and correlation -1. And so if I'm like a risk manager and I have no information, I still, however, may think that my worst case correlation is, it's better than 1 or -1. And so that's kind of what intuitively justifies this assumption, is that the worst case is not this kind of co-monotonic case where our unknown random variables are kind of exactly correlated with each other. And in terms of how we put this into the optimization program, well, we're optimizing over W as a function of Y and Z. And so we simply add Lipschitz constraints on these weight functions in the linear program. And so that's kind of computationally handleable. And the kind of more difficult thing to think about is what happens when our protected attribute is multiple valued, which is, of course, really important in practice. But what we're doing is we're maximizing and minimizing disparities. So in the binary case, that's the worst case disparity for one group against the kind of best case outcome for another group. However, if we have multiple groups, we now have this kind of multi-objective problem. And so a kind of common strategy for multi-objective problems is to simply consider scalarizations of the objective functions. And so the way we're going to think about multiple valued protected attributes is that we're going to consider a set of pairwise disparities. So we're going to fix a reference class. Here it's going to be A, and we're going to measure disparities with respect to this reference class. We're going to introduce the scalarizing weight vector row. We're simply going to sum up these pairwise disparities and optimize it. So this is a common strategy for multi-objective optimization. And now our partial identification set is going to be a set of all of these pairwise disparities. And I just wanted to pause for any questions. Okay. And I'll kind of try to briefly talk about estimation and computation before concluding with some of the case studies. And so in this most complicated case where we have a kind of like a hard estimator and additional modeling assumptions, it's really a case if we want to consider multiple valued protected attributes. We have an algorithm for this in the paper that reduces to a linear program and a grid search. And I'll try to kind of briefly explain the intuition. So previously, I showed these kind of rectangular sets for the partial identification sets. So if we only have two groups, these sets are actually intervals. So I'm going to skip around a little bit. So the worst case and best case disparities for two groups is simply an interval. However, if we have multiple value protected attributes, that's when we obtained these kinds of sets that have volume when we look at this pairwise parametrization. And now how do we actually represent this set? Well, what we can do is we can optimize over these linear combinations. And so we're going to use the support function representation of a convex set. So a convex set satisfies certain properties. It's the intersection of all of its supporting hyperplanes. And so you can think about the convex hull of a set. And this mathematical representation simply states that it's the intersection of its supporting hyperplanes. And it turns out that this optimization problem that we wrote down allows us to compute the supporting hyperplanes of a convex set. So what we do is we simply sample many different weight vectors, optimize the disparities according to the scalarization, and then take the convex hull of these resulting hyperplanes. And that's how we kind of obtain these more, that's how we obtain these rectangular sets. And then another kind of main consideration is that, of course, confidence intervals are really important. So all of the sets that I've talked about kind of assume that we're working with infinite data. So we take these data sets and we learn an outcome model, probability of y equals 1 given z, or probability of a equals 1 given z, but we assume that these are the true probabilities. In practice, this probabilistic estimation also introduces uncertainty. So a kind of an auditor might ask, you know, maybe your conclusions are just due to finite sample uncertainty. And so we study this problem of statistical inference. And I'll just kind of briefly summarize the results which are in the paper. So in the case of closed form bounds, this fact of nuisance estimation introduces some technical difficulties, but we're able to derive a de-bias estimator that allows you to compute closed form variance and compute confidence intervals. Otherwise, if we're just solving general linear programs, under some assumptions, we can show, we can tell you how to kind of like bootstrap for a confidence interval, but we aren't able to provide closed form variance. So that's a summary of this kind of question of statistical inference. And now I'll talk about the case studies. So here we have a case study, which is trying to illustrate the setting and lending, but we're not trying to like replicate any particular analysis. There are other considerations that you might want to take into account. So in the US, it turns out that there is a data set. So mortgage loans do record race information along with the loan outcome information. And we use this data set to kind of benchmark a simple proxy. So we learn a proxy model that's based on income and geolocation using the community survey. And this case study, I should say, draws a lot on Charget's work in that previous paper I mentioned. And so these are the resulting pairwise intervals. So here we're looking at demographic disparity. So what is the probability of, we're like, what is the proportion of loans that are granted to members of different races? And we have 3 levels of the protected attribute. We have white, Black, and Asian or Pacific Islander. And in this setting, we turn this 3-valued protected attribute into pairwise disparities by doing a kind of one versus rest comparison. And so we look at a proxy that's trained with only income versus only geolocation versus the combination of them. And so the main takeaway is that these sets are relatively large. They cross 0 and they span like, some of these span like on the order of like 1. And so the range of the disparity is maximum 2. And so again, this is the partial identification set that's consistent with this proxy method, but without making any assumptions on any estimation procedure. So it could be the case that you choose a certain statistical estimator that will return a point in the set. But this kind of the main kind of like takeaway is that these particular proxies are not super informative. That's not terribly surprising because we're only using income and we're using very coarse geolocation survey. We're just using county information. And so, you know, if this was the partial identification set, it suggests that you should actually invest in either kind of like more predictive proxies, or it might be worth to investigate alternative approaches for estimating disparities. And so the next case study is going to be a very different setting. We're going to look at personalized medicine. And so it could be, of course, very interesting to kind of assess personalized medicine algorithms to see whether or not they have differential performance across different race groups. And we're going to consider a specific data set of warfarin dosing that has been kind of widely studied in the past. And we're going to look at this task of warfarin dosing for diabetes. And just to recap, what is the mapping between the warfarin variables, we're going to let y be whether or not the actual dosage is high or not for an individual. We're going to let y hat be the estimated dosage, whether the optimal dosage for this patient is a high dose or a low dose from a kind of generic prediction model. We just use a lasso model. A is race, and our auxiliary information is current medications, genetic factors, or both. So in this warfarin data set, we have all four of these types of information, but we're going to artificially consider the setting where we only have a main and auxiliary data set. And so here is the here is the diagram of the set of disparities. On the x-axis is the TPR disparity for white versus Asian. On the y-axis is the pairwise disparity for white versus black. And again, we're looking at proxies that become more informative as we move to the right. And so what's kind of interesting is that there are genetic biomarkers in this data set. And perhaps unsurprisingly, genetic biomarkers are a better proxy for race than just the medicines that have been previously given. And when we combine both of these types of information, this actually shrinks this last set quite considerably. And now the x-axis disparity is definitely positive, which suggests that the true positive rate of this dosing algorithm is definitely higher for whites versus Asians. However, for whites and blacks, it's not so conclusive. And so this illustrates that small partial identification sets, if we have informative proxy information, can rule out the absence of disparity, even if we only have access to these proxy methods. And so with that, I'll conclude. And I guess just to conclude, the question of the paper is trying to characterize the limits of what can be concluded using data combination. It's of course really important to audit disparities. And so that's why we kind of overall suggest you should know how much you don't know with these proxy methods, rather than kind of being too quick to use just like a single estimator. Yeah. Thank you.
Well, thank you, Angela. I'd like to open the space for questions from the audience right now.
I have a question about the non-binary case. You're saying that you'll calculate the disparity with a fixed class iterating over the other classes, right? But then there's a parameter, and you said that you optimize the disparity with respect to this that parameter. What does that mean? What are optimizing?
Yeah, that's a great question. Let me try to pull up that slide again, maybe.
Yeah.
Is this the right slide? I'm not sure.
Yes.
Okay.
Yeah, that's the slide.
Yeah. So that's absolutely a great question. So, in the setting where this weight vector is just 1 somewhere and 0 everywhere else, that's the same as just optimizing a disparity between 2 groups. So that's the kind of base case to think about, is that a one-hot weight vector is just a pairwise disparity. Now, if we have weight vectors that are, that do not identify binary disparities, that are just kind of, what does uniform mean? In that case, I think the multi-objective optimization analogy is the best one. So you're simply kind of reweighting these disparity objectives. But I agree, it's really hard to interpret what that means. So I think like the main proposal for multiple value protected attributes is not to kind of optimize a single weight vector, but really to try to report out this set. And so this set is obtained by essentially sampling different values of the weight vector and observing what is the maximal disparity in that direction. And so this helps illustrate the picture of what are all of the possible disparities that are possible. But I agree it's hard to interpret. So it's harder to interpret for a single weight vector what that means.
Mm-hmm. Okay, thank you, and congratulations for your talk.
Thanks.
I have a question that just occurred to me, but not necessarily, it's more like have you thought of it? Because I think that the same framework could be used like if we couple with for example, as we do here when we are auditing and trying to understand our algorithms, we use those explainability measures. As I think we had talked before, we use a lot of shape values for do things here. But my question is, have you thought about like coupling the same idea, but instead of trying to reflect on the outcome of the algorithm, maybe like coupling the same idea, but trying to understand this kind of input, this explanation, how because that's the thing. I think we have that. I'm thinking about an experiment I was performing, because we have the same situation. Like we have these attributes that by its explanation we see that it has it appears to have like a really disparate impact on the model. And what I'm thinking is we could just like use the shape values, for example, as the outcome of an algorithm.
Mm-hmm.
For example, now we can understand for this class of algorithm that has a relation with like race, for example. I think we could just like try to understand how it's treated by the algorithm. So inverting the questions to talk about treatment as well, like coupling these things together. I don't know, have you thought anything about it before or something similar? I don't know.
Yeah, that's a really great question. Like how to kind of incorporate more of this model-based information, because we're essentially just working with the model outcomes rather than the model itself. And so I guess it really depends on how the explanation is parameterized. So kind of in theory, for anything that you can write down as this kind of nicely in this optimization problem, it might be doable, but often these kinds of explanations might themselves be like the products of some statistical fitting procedure or another thing. So it kind of really depends on like which part of the model process you want to embed in this. And I think this approach is pretty heavily reliant on optimization. And so that may be the limiting factor, I think. But that's a really good question.
Okay, but maybe we can talk more about these later. I'd like to.
Yeah, for sure.
Anyone else? Well, so I think we can wrap it up then. So thank you very much for talking to us, Angela. Thank you for this very clear introduction. I think a lot of I myself would take a better dive into the paper to get those details, but I hadn't yet get a full read on the paper, and this was a very nice introduction and so for a very complex theme and a lot of complicated ideas. So thank you very much for being so kind and wrap it up so nicely. And thank you very much. And I hope we stay in touch.
Yeah, thank you so much. And thanks everyone for listening. It was really great to talk about it. And yeah, if there are any questions, please let me know. Thank you.
Thank you, Angela.
Okay. So, bye everyone. have a nice rest of the day.
Thank you.
Bye-bye.
Bye.